Remember the ice tables?
We're cool with that? Yeah, what's up?
So is the bell book the one we're supposed to have for this course?
It's out of print. So I'm just telling you where these notes came from.
Okay, because like I know the bookstore had a different one that I bought, and I didn't know if like I was having the wrong book.
No, it's just essentially it's for reference, you know, for the vocabulary words and the things and some extra work for problems and so on. But yeah, the bell book is where the examples came from, like the amphetamine example and the cocaine example that we did in the last section and so on. So I've moved a few things over to the new book, but it just takes a long time to get it switched over. Yeah, but I wanted to continue with the bell book because it was a good one. It had just the right depth, according, you know, to my opinion. But they just quit printing it. I don't know why. They went for 2 editions and then they didn't do a third. So yeah, which is unusual. I mean, if you think about your background in chemistry, you know, the traditional chemistry degree, those books. We're in Atkins. We're in the 12th edition now, or the 11th edition, and I'm reviewing the 12th edition for Oxford University Press. And so, you know, those traditional classes, inorganic, biochem, and so on, you know, they're taught at every university all the time. But since forensic chemistry is not one of those traditional disciplines in chemistry, you're not guaranteed to get a 3rd edition, a 4th edition, a 5th edition. So that book, for whatever reason, the publisher, maybe it wasn't selling. So. And then I didn't find an exact replacement, so it's still kind of in the air on that. So that's the story on that.
All right. I just want to make sure.
Yeah, that's right. It was a great question. Yeah. And so we're going to talk about partitioning, but the main tool we use for partitioning is acid-base equilibrium. So this is in the sort of category of sample preparation. So we. You know, in our examples in the last section where like you get these little cocaine seizures, little packets of cocaine, you think it's cocaine, but it's not pure. So there's a lot of other stuff in there. There's cocaine, there's caffeine, there's procaine. Those were active ingredients. There's also inactive ingredients, things that stretch the supply. So you don't want to give out pure stuff because it doesn't look like very much, right? And you're looking at it, you're like, you know, give me more. Like, well, no, this is the really pure stuff. And so you stretch it a little bit so they feel like they're getting more. That's if you look at a tablet, it's a 200 milligram tablet. That tablet does not weigh 200 milligrams. It's a lot larger than that. And there's some psychological thinking involved. I mean, why would we want to do that? Well, you know, if somebody looks at a tiny little tablet and they got a raging headache, they're like, well, that ain't going to do anything. So they end up taking 4 or 5 because this is a bad headache. Well, that's not good. Okay, so the active ingredient can be really small, but then they stretch it. They'll add in things to make it look larger. They'll also add in buffering agents, things that help not upset your stomach and stuff like that. So they'll take care of you by expanding the preparation, the formulary, to have these other things. A lot of times it's pH control, but not so in like illicit drugs. It could be anything in illicit drugs. It could be talcum powder. It could be coffee creamer. I mean, it could be anything that's white that will stretch that powder out. So for sample prep, you've got to get your analyte out from all of that because no one's going to jail for coffee creamer in their nose, you know. Right? So you don't care really how much coffee creamer is there. You want to know if it's an illicit drug, if it's cocaine or what have you. So a lot of times the matrix is irrelevant, and so you can just dilute it and shoot it onto your instruments, but a lot of times you have to separate your analyte. And so you have heterogeneous systems where you've swabbed the surface, and so now the analyte's on the swab. How do you get that into a GC? Well, you've got to get it off the swab, and so you'll wipe down and then you'll extract the wipe. So you put the wipe in a vial and you put in a solvent and shake. And then this analyte has moved from the stationary phase into the mobile phase if it's really soluble. And now then you can take that liquid and then analyze that. And so homogenization, sometimes the drug, like if you have tissue, that's the simplest example of homogenization. So you have things in muscle tissue or fat tissue, and you want to get that analyte out. You can destroy it with a little blender called a homogenizer, and so it just destroys the tissues and releases all the chemicals on a molecular level. Or you can use ultrasonic homogenization, or even sometimes acid digestion. We put things in strong acid and it just destroys all of the matrix tissues and also the If it's in a mineral, it destroys that. And then you have large, field samples. We talked about the sampling plan where you come in with a large seizure and then you decide on, 20 plus 10% of the remaining, and you take those and then you make your lab samples. And so even then, a packet this big is probably still too big to analyze, and so you're going to take that, dilute it, and break it into your replicates and so on. And so then when we start separating in the liquid phase, we get into liquid extraction. And we want to pull the analyte that we're interested in away from the things that we don't care about. So, all of the, if it's a tissue sample, we're not interested in the membranes and the proteins and the DNA and all of that. We want to get to the analyte of interest. So we can separate it from the matrix, or we can separate it from interferences. So if we have something that would mask the signal, and if we can get our analyte away from that thing that's going to interfere with our signal, then that's going to be a fantastic step that we have to do, or get our analytes away from all the other analytes. So in order to do this, we use Le Chatelier's principle. So that's why I have a taxi there. So Le Chatelier's taxi will take our analyte from one phase to the other, from the organic phase to the aqueous or back. And so we're just using this principle that we learned in Chem 2 to drive our analyte from one side of the barrier to the other so that we can analyze it and separate it. And so this will we'll use the pH and an acid-base equilibrium to drive this partitioning. So we have this generic reaction with the generic equilibrium constant. So you should be very familiar with this, but let's go over the basics. It's products over reactants. Okay, so we can remember that. It's always comfortable to go that far back. And so we have the concentrations, and that's another thing too. You never know what people don't know. I had a student years ago who did not know that the square brackets meant concentration. So you think about that equation. If you didn't know that those meant concentrations, it's meaningless, right? And those little A, B, C's, and D's, those are the number of moles from the balanced chemical reaction. So you have to have a balanced chemical reaction. If you don't have a balanced chemical reaction, you don't have a good equilibrium constant. Now this is a concentration equilibrium constant, so we'll be using concentrations in molarity, but it could be other concentrations. But this would be, traditionally the ones that you look up in the tables and so on are based on molarity. And so when the equilibrium constant is much, much greater than 1, that means the numerator is much, much greater than the denominator, which means the products are much, much greater in concentration than the reactants. And vice versa, if K is much, much less than 1, then the reactants dominate. The denominator is huge, the numerator is small, and so you have all reactants. And so this allows us to understand how we might drive things to the reactants or drive things to the products. So if we know the equilibrium constant for a particular reaction, then we can choose which side we want to be on, and we can use acid and base to drive it forwards or backwards. So this is a survey of pH, of a lot of things that are related to household items and bodily fluids. So right there in the middle, around neutral pH, we have human blood and tears and other things. It just kind of doesn't go together. Maybe it does. I don't know. But yeah, so pH 7, neutral. So that's why things burn your eyes a lot of times. You get soap in your eye, and if it's not pH balanced like Johnson & Johnson baby lotion or baby shampoo, then it really burns because it's a different pH, and your eyes are saying, "What the heck is going on?" Equilibrium's out of whack in your eyes. Things similar to that are milk and saliva and egg whites, again, natural products related to living things. But then you start getting further away from natural things and living things. You get to the really dangerous stuff like black coffee. It's a pH of 5 range. Then you get into tomatoes, which are pretty acidic, and then wine. Cola and vinegar up there at 3. And how many people have seen those emails or posts online about how dangerous Coca-Cola is, right? Tell me some of the things you've heard that Coke does.
Like used for like cleaning blood.
Cleaning your car battery.
Cleaning your car battery, cleaning up blood, soap scum, it'll rust off a penny. Yeah, I mean it's crazy bad, isn't it? You know, like soap scum, that stuff is impossible to clean. Pour a little Coke on there, and it just chews it all up, right? And then so they make it sound like you should never put this in your body because it's so corrosive, you know. But look at gastric juice. That's a pH of 1. That's 100 times more acidic than Coke. You know, and so they're like, don't put that in your stomach. Oh, wow. Well, gastric juice is a pH of 1. You know how to clean up soap scum? Throw up on it. It'll come right off. Yeah. So, and they're like, Coke, it'll dissolve meat. Well, throw up on meat. It'll dissolve meat too. In fact, that's the purpose of it, because you put meat in your stomach, and what happens to it? It gets chewed up by the gastric juices. And so, again, it's this hype that people do all the time. It drives me crazy. And they don't really know the full story. Yeah. And so let's go to the other end of things. Baking soda, very, very similar to neutral pH, but it's about, 1/100th of the acidity, it's 100 times more basic. If you have, stomach acid, bad tummy, because of your gastric juices, you can drink milk of magnesia, which is a pH of 10. That's pretty basic stuff. It's like magnesium hydroxide, and so it's the formulation of magnesium is not too bad for you. So you can drink that. Don't drink other kinds of hydroxides. The metals typically will get after you. And then household ammonia, close to pH 12. And then household bleach, a lot of times it's the sodium salt of hypochlorite. And so it's pretty basic because they've taken the protons off and put a sodium on there, made a salt out of it, and then you can make a solution of that. And then that's pretty basic. And then sodium hydroxide, pH 13. That stuff is really bad. It's damaging to proteins. So you get base catalyzed hydrolysis of proteins, and so it will attack your skin. So any of the basic materials like sodium hydroxide or even trisodium phosphate, which is a sort of binding agent in concrete, will suck the fat out of your skin and saponify it and make it feel soapy. So you'll get that fat, it'll turn to soap, and that's how they made lye soap. They mixed in lye, which had sodium hydroxide in it, and they would mix that with fat, animal fat, and heat it up, and it would make soap. And then you could cast it into bars, and you had old-timey soap. They made carboxylic acids out of it, and so then you had this carboxylic acid-based soap, which would precipitate with calcium ions. So that's why we wanted to get away from soaps, and they went to putting sulfate groups on organic molecules, and that's your detergents. So the difference between a soap and a detergent is carboxylic acid versus a sulfate. And so that's pretty cool. But you don't want it to precipitate with calcium, because if you have soap and you have hard water with lots of calcium, then you're going to have a lot of soap scum, and it's going to precipitate out everywhere. You'll have rings in the toilet, rings in the tub, rings in the sink. You'll have a lot of precipitated calcium, carboxylic acid, organic molecules. Sodium hydroxide will suck that fat out of your skin, and then it will also hydrolyze the proteins and damage the skin. So if you have really concentrated base on your skin, it can eat right through it. And so that's pretty bad. I would rather deal with acids than bases. I don't want any kind of bases on my skin. And you may have experienced that too. If you picked up a beaker with some base in it and it was a little dribble on the front, you got it on your thumb and you didn't have gloves on, you had to wash it off for quite a while. I patted some concrete down. I put in a basketball goal and made the concrete, and then I made it look real nice on top, but I didn't have gloves on. Duh, stupid. Okay, and I thought it's just for a little bit. Right? Washed it off, and I thought, man, I may have done something wrong here. This feels pretty soapy, and so I got it all off, and my skin dried out so bad. Like it pulled all the lubricating fats out of my skin, and the skin shrunk. I couldn't stretch my hands out. Like I couldn't straighten them out for a day or so until I generated some more skin and some more fat. Yeah, and so it was pretty bad. I was like, man, I'm not dumb. and the skin was so dry, it looked like I was 100 years old. Wow, this is what I'm gonna look like. And so that was not very happy either. And Jennifer was like, "What's wrong with you?" Nothing. So I knew that I had done something stupid. So watch out for the bases. Okay. So some of the acids are polyprotic, and it kind of depends upon which direction you're coming at it. I mean, things are acid or base, kind of depending on which side of the equilibrium you're on. But the nice thing about this is most of the polyprotic acids, they're Kas, Ka1, Ka2, these are the acid constants, are more than 10 to the 3 different. And so if that's the case, you really don't have to deal with the competing equilibria, that you just get one proton at a time. And so you can write out the reaction where it just reacts with one water and gets protonated, okay, or deprotonated. So you can look at these, like citric acid, it's got 3 here. Oh, I'll pick the one that has 2, it's not 10 to the 3 next to each other. So let's look at like phosphoric acid. You know, the first proton is 7.5 times 10 to the minus 3 is the Ka value. And if you want to take the minus log of these, essentially the minus log brings that exponent down. And so this is close to 3. It's 7.5, so it's almost 4. So it'll probably be a pH of about 3.5, 3.7. So you can look at these and kind of figure out what the pH would, or the pKa would be. So that would be a pKa of about between 3 and 4, a little closer to 4. This would be a pKa of between 8 and 9, right? 6.2 times 10 to the minus 8. So it's almost, 10 to the 10 to the minus 9 would be, 10 to the 10 to the minus 8 would be 10 to the minus 7. And so this would be a little closer to between 7 and 8. And so maybe this one would be between 2 and 3, actually. And then this is 10 to the minus 13, and so this is 4 times 10 to the minus 13. So it would be really basic, a pKa of about, between 12 and 13. 4.2 on a log scale might be closer to the middle, so it might be a pKa of 12 and a half. And so you can look at these, you can put them in your calculator, get the log key, change the sign. But those are 3 orders of magnitude different between them. And so you're really, for phosphoric acid, going to deal with 1 proton at a time. For citric acid, it's a little more complicated. These two being that close, you might have some competing equilibria. Okay, but for this class, we're just going to deal with the protons one at a time. So all our reactions will just be acid and water making a hydronium ion and a conjugate base. Okay, or the reverse of that, a base plus water making the protonated base plus hydroxide. So let's get into it. Let's look at an ice table. So this will be the kind of pH type problem. What's the pH of a 2 molar solution of amphetamine? We will get to the drug flashcards in the next section of the notes, or maybe closer to the end of this one. And so you'll get sort of an idea of how to recognize some of these structures from those drug flashcards. If you want to get ahead of yourself, you can go on and find those on Blackboard and print them off, cut them up, and then you have your little flashcards for the drug structures. I'm not asking you to draw them from the name, but I'm asking you to recognize them, okay? And so you should be able to recognize, like if you see that drug structure, oh, that's methamphetamine. Or if you see this drug structure, oh, that's cocaine or cocaine related. So at this point, you don't really need to know the structure or even the formula. What you need to know is that 9.8. That's the pKa. That's telling you the acid-base interactions for this molecule. Now, what's interesting is you see that word amine. What's that tell you? Nitrogen. And what does that tell you? It's basic. Yeah, amines are basic. So this is a base. But we always list pKa's. Okay, so this is a trick. You've got to understand the balanced chemical equation first before you do anything else. Are we dealing with a base or are we dealing with an acid? That's your first question. And this is amphetamine. This is a base. So you look at that, you really zoom in on this idea here. When you see amine, you know it's a base, but this is a pKa. So big question mark there. What do we do with that? So let's go to the balanced chemical equation first, and we're going to just write this as a generic base, B. So amphetamine, B, it's a base, plus water. So we have a base, which is amphetamine, dissolved in water. It's going to react. It's going to be protonated to make BH plus aqueous and hydroxide ion in aqueous. Okay. Notice here, this is the ionized form of the base. It's a product. And the ionized form of the base is going to be soluble in water, aqueous, more soluble. The deprotonated part, we have it in aqueous solution here, but if you give it a chance to go into the organic phase, if it's deprotonated, if it's just an organic base, it's going to go into the organic phase. There's nothing that water really wants from that molecule. It might be a little polar, but it's not charged. So water is going to hold on to the charges. So that's the principle of all of this. We try to find how to make it ionic. If we make it a BH plus, then it's going to be favored in the aqueous phase. And then if it's not, it'll be favored in the organic phase. So it's going to go to one or the other. And that's what I'm talking about with Chatelier's taxi. We're going to push it either to the products. In this case, we push it to the products. We're going to push that base molecule into the aqueous phase. And if we push it into the reactants, we're going to push it into the organic phase. And we just use pH to do that. We'll dump stuff in there. We'll dump in hydroxide or dump in acid, and it'll push it either way. But for this point, we just have it in water. So we just put 2 molar, which is ridiculously concentrated, but it's just an example. 2 molar solution of amphetamine in water. What's the pH? So let's figure out how we can get this pKa to be compatible with the basic reaction. So we have pKa, but we need pKb. Okay, and so we have this relationship Kw, because this is in water. That's the governing equation. The ionization constant for water governs this, and it's Ka times Kb gives you Kw. And then you can take the minus log of everything. That's mathematical, if you do it to both sides of the equation, you're okay. So you take the minus log of both sides of the equation, and you end up with pKw equals pKa plus pKb. So you could just take pKa and subtract from 14. Okay, because this is 14. This is 9.8 plus pKb. See? So that's pretty easy. So we could figure out our pKb, and then we could raise 10 to the minus pKb, and that'll give us our Kb. So here's our Kb. It's this right here, this number, 6.3 times 10 to the minus 5 is Kb. So now we know what Kb is, and we also know what Kb is algebraically from our chemical reaction. So we know it's the concentration of our BH plus times the concentration of OH minus divided by the concentration of our parent base. Okay, so we have our equation, and we want to know pH. So how are we going to get to pH? It probably makes sense to get POH and then subtract that from 14. So we're going to work in base all the way through. We're going to get POH, and then POH plus pH equals 14. So let's set up our ice table. I'm going to give you a minute or two for you to try this on your own. So if you've got the notes, don't cheat. Try to do this cold, all right? I've got the ice table there. I've set up the first row. I shouldn't have. I should have left that blank. But you take a minute or two and get started on it. a long minute. We got one more. Okay. So if you look up here, you can kind of follow along. If you haven't finished, that's okay. Just kind of see if you were on the right track. That's the main point. And so with that ice table, we have some of the reactants disappearing and they show up on the products. And the coefficients of these would be the same coefficients that you have in the balanced chemical equation. So if you had a two hydroxides produced for every one of these molecules that went away, then it would show up as a 2 on the hydroxide column. But like I said, most of these acid-base equilibria have just 1s in front of all of the species. We're doing this 1 proton at a time. So even if it was a base that could accept 2, we would write our equilibrium where it was just 1 proton at a time. And so most of the time we're going to have, in fact all of the times, we're going to have just X and plus X and minus X on these things. Now, look at the signs. On the reactant side, we have a minus X. On the product side, we have a plus X. And don't worry about the X as much as you're worrying about the chemical species. If you look at the column headings, that's what makes sense. If we lose a B, we get a BH plus. Where did that H plus come from? It came from water, and that's where we get the OH. We don't show water in this because water is the solution. So we have as much water as we want. So it's participating in the reaction, but it's not included in the equilibrium constant because it's a constant. We're not changing the concentration of water in water. So these are all concentrations of that substance in water. So the concentration of water in water is constant. So we just sort of have lumped that into the constant. So instead of having 2 constants in our equation, we just bring water over in, we just have 1 constant in our equilibrium. So then we make an assumption that this is not a very strong base, and so very little of it is protonated. It doesn't. It's an organic molecule. It's not a super strong base, and so very little of it actually shows up on the right. And so when we subtract a tiny little X from our 2.00, we don't notice that any's gone. Kind of goes back to the significant figure convention. If we're subtracting a number that's below 0.01, we could do the subtraction, but then when we round to the hundredths place, it's going to come back to 2.00, and we will not have noticed that anything's missing. But over there on the right, where we have 0 initially, anything is going to be significant compared to 0. And so we're not saying that X is insignificant, we're saying X is insignificant compared to 2. And so we have this equation. We put everything into our equilibrium constant expression. The top 2 are both X, and so we end up with X squared. We have 2 on the bottom, and so we can solve for X, which is our concentration of hydroxide ion. And this is just a reminder here that our Kw is our governing equation because that's the ionization constant for our solution. And we have the concentration of hydroxide times the concentration of hydronium ion, and if we take the minus log of all of those, then we have POH plus pH equals the pKw. So that allows us, let's just solve for POH and then subtract from 14 to get the pH. So here's our solution for the hydroxide ion concentration, that is X. We have the 2 moved over to the other side, we take the square root, and we end up with this. Oh, good. No viruses. So this is our POH. Actually, not the POH, it's the concentration of OH, and then we take the minus log of that, and we get the POH. So the minus log of that number, so our POH is 1.949, and so we subtract that from 14, and we end up with 12.05. So how did you do? Did you get started okay on that problem, and is a good review? Yes?
Can I always make that assumption?
No. The next one we're not going to be able to. So let's look at one where that concentration of amphetamine is small enough that our assumption would fail. Another thing too is we calculated the concentration of hydroxide right here. This is our X value. So let me get everybody's eyes on this one. This is our X value. And so we can go check our assumption. So let's take this, if we looked at that, we could take that X, let me find my pen. We could take this X right here and plug it in to right there and see if this assumption works. So you can check your work. If you make the assumption and you say it's insignificant, and then you go look at it and you go, whoa, wasn't really insignificant, you know. And this is now 0.0, it's 1 times 10 to the minus 2, so it's 0.01. So it might show up. I mean, it would be right here, so it would be 1.99. And so then you could just iterate this. You could put in 1.99 and redo the calculation and see that X is a little bigger. So, you know, if you had Excel, you could just make a bunch of rows and just grow X of, you know, a tiny little amount from 0 up to whatever, and you could solve it numerically if you wanted. Okay, that would be what you would do if it was a really complicated problem. You know, when you had multiple species, essentially you had one equation but 2 or 3 unknowns. You could just use X as your variable and run it in a table until you get your equilibrium constant. And so you'd have a calculation of Q, which would be your equilibrium quotient or your reaction quotient, and then when Q equals K, you're at equilibrium. So let's look at a situation where that assumption would fail. So 0.0025 molar solution, much, much less concentrated. What would be the pH that results from this? We have the same reaction, okay, and the same ice table, but we have a different initial amount, 0.0025 molar. Okay, so did you get the table written out? So that's the initial row. Then here's the change row and the equilibrium row. So minus X plus X plus X, that's the same. But for equilibrium, we're going to keep that 0.0025 minus X as our reactant at equilibrium. And so what do we do with that row? Well, we go ahead and make the equilibrium constant expression. We have products over reactants. And so here we can get rid of that denominator, multiply both sides by the denominator, then we multiply K through, and so we end up with a quadratic equation. Oh, come on. This thing's getting worse and worse. I have to buy a new one. Okay, so this is our quadratic equation, but it's not in standard form. So we multiply the 6.3 times 10 minus 5 through that parenthesis. I just didn't leave out any steps because I wanted you to follow it along. So. All right, so then there it is in standard form. So we have 0 equals x squared plus, so it's ax squared plus bx plus c. C is negative in this case. So that's our standard form for the quadratic equation. And then we go find that quadratic formula, or we sing the song. I never learned the song. Did y'all learn the song? Does anybody know it? Don't be bashful. Yeah, there's some song that people sing. I don't know. Yeah, here it is. So that's the standard form on the left with your coefficients A, B, and C and the definitions of those. And then you have x is equal to minus b plus or minus the square root of b squared minus 4ac over 2a. And so you just look up at our equation, which is in standard form, and you define what a is and b and c. Put it all in that equation. And you solve for x, which is the concentration of hydroxide ion and the concentration of our protonated base. So it's not too difficult, it's just tedious. Once again, something that's not hard, but tedious. You know what to do. Go ahead and hack your way through it and get the thing in standard form and make sure you don't drop the negatives and stuff like that. Pay attention. So here's the x plus, and you have x plus and x minus. So you have two roots here. And so always put a little subscript on there to keep track of which one was which. So I put an x plus for when I use the plus sign, and I put an x minus for when I use the minus sign. So there are my two roots, which would be the concentrations of hydroxide ion. But we've got to make a decision. And so what do you see that would help us make the decision? Yeah, you see that negative sign on the x minus. So we end up with a negative concentration. So that's pretty amazing that we put amphetamine in our beaker and that beaker goes over to the shelf and finds some more hydroxide and takes it away from somebody else and pulls it in. No, that doesn't make any sense. So it's a negative, actually it's negative concentration. So it somehow gets the hydroxide to leave that flask and go elsewhere. At 2 moles per liter. No, that doesn't, negative concentrations, we can't get our mind around that. That doesn't make any sense. So it has to be a positive concentration. So the positive root is the only one that we hold on to. Okay. Now, I've never seen a problem, but I guess theoretically it would be possible where you have 2 positive concentrations. In that case, it may be that you have still a nonsensical answer. So if I'm looking at my problem here and I have 2 concentrations possible, those are x. Remember, those are x. And I can't have an x that's greater than 0.0025. So that would be a nonsense root as well. So x has to be between 0 and where it came from, 0.0025. And so if there's an x out of the top bound too, it's nonsense as well. So don't be afraid of making this decision. Look at it, and that's where the critical thinking comes in. I know that people don't like branching problems. I got 2 answers. What do I do? Well, look at it. You know, it's like you're hiking down the road. I got a fork in the road, but that one, the road stops and goes off a cliff. So I'm probably not going to go there. I'm going to go here. It's a lot easier than you think. And so this is the negative concentration. We throw that away. So we use this 0.000367 as x. And so then we get our POH minus log of that number is 3.44, and we end up with our pH 14 minus that is 10.56. So it's a lower pH. It's not as basic. We don't have as much amphetamine in solution, so it's 100 times more acidic or 100 times less basic. Let's check our assumption. We can put this in there at this 0.00036 and subtract that from the 0.0025. And so these are our numbers at equilibrium. So that's how much base is unprotonated, and this is how much base is protonated. So this is the percent ionization is this number. How much of the base is ionized? Now, whenever you're doing percents, what's another way to say percent, right? Part over whole. Okay, so always remember, percent is a part over a whole. And you want percent ionized, you want the ionized part on top, and the whole goes on bottom. For some reason, people put this on bottom, down here. But that's not the whole, is it? That's the amount of unprotonated base still remaining. This is the whole. That's all the base you came in with, and now this amount is protonated. Okay. So this is 14% protonated, or 14% ionized. Okay. If you wanted to get that into solution, that's probably not very good. I mean, only 14% of that is going to go into the aqueous phase. take a snapshot of it. But anyway, calculating percent ionized is this over the apparent amount of base. So that's an example where that assumption fails. Many times we're dealing with buffered pH. So buffered pH means we're controlling the hydroxide or the acid concentration, the hydronium ion concentration. And so we would have a number here, an OH number here, if this was buffered. And that would really govern the equilibrium, because it doesn't matter how much of our tiny little amount of analyte comes in, that's a buffered hydroxide ion concentration, and it's going to absorb any excess acid or get rid of any excess base. It's buffered to be that pH. And so this number will be given to us if it's a buffered situation. And so X will be really insignificant. And so we'll just have one X in our problems. So it'll be really easy when you have buffered situations. And what are we dealing with a lot of times? We're dealing with our stomach and our colon. Those are buffered situations. The body buffers the blood, the body buffers the stomach, the colon. All of our pHs are buffered. That's how our body controls them. So, okay, so let's look at this buffered situation. We take the concentration of neutral amphetamine, how much remains in acidic solution of pH 2.0. So we're putting in a particular amount of acid. And so we're going to write this a little differently because we're putting it in a buffered pH. We'd like to have a place where the acid shows up. Notice in our previous reactions we had only hydroxide. And we could do this problem with hydroxide, but let's look at it with acid. So let's rewrite that equation. So now we have the base, the parent base, reacting with hydronium ion, H3O+, giving the protonated base and water. And so now in our ice table, notice the double-headed arrow is in a different place. The two columns on the left are both reactants, and we only have one product column. You see how that's different than what we had? We got to kind of move fast because we have 5 minutes before the duel of the fates. And so this is the point here, if BH plus was what we were analyzing, then we want as much of it as possible. So we want to drive this reaction to the right as far as possible. And so if we want to protonate that base, it makes sense to put it in contact with an acid that's going to donate those protons. Remember that an acid is a proton donor. That's one definition of an acid. And so we want to put a lot of proton donors in solution so that when they see the base, they go, hey, have my proton. This is my life. I live to donate my protons. And so here we have that 0.0025 molar base. Put it in with 0.01 molar hydronium ion and do the ice table. Minus X on. Notice both left X's are minus. The right one is plus because of the way we've written the reaction. And so what we've done is we've driven it all the way to the right. And so this is a nice little tool to not have to deal with the quadratic equation and all these tiny little numbers. We're going to put it in contact with acid, drive it all the way to the right. And how do I make it go all the way to the right? I take that base column to 0. So if this goes all the way to 0, that means that X is equal to 0.0025. And if X is 0.0025 for this spot, it's the same X all the way across. And so in BH plus, I have 0 plus X gives me this. And for the hydronium ion, 0.01 minus that equals 0.0075. So I have a new initial. And why do I want to do that? Because I wanted to go backwards now. Let's drive this reaction all the way to the right and see how much or how little it goes back to the left. Okay? And so now I'm running the reaction in reverse because nature hates a 0. Right? You see that 0 up there on the new initial row? Nature's not going to let that stay around very long. But we mathematically can drive it all the way to the right and then have it squeak back just a little bit. Okay? And so now we have a new equilibrium. We have that 25 minus X. X is so tiny we don't notice any gone. And the 0.0075 plus x, x is so tiny, it's insignificant. But 0 plus x, anything plus 0 is significant. And so we have just one x in our equation. We have Ka, 10 to the 9.8, minus 9.8, x, 0.75 and 25, and we can solve for x. And we're wanting to know, this concentration of neutral amphetamine, how much of this B, neutral amphetamine, remains. And so that's our x. So we'll calculate x here, and it's 5.3 times 10 to the minus 11. Tiny number. We could have been forced to use the quadratic equation on this one up at the top, but let's just drive it to the right and come back a little bit. So this is another way to avoid having to use all of the minus b squared and 4ac and all that stuff. It's just drive it to the right and see how little it comes back. And then we're just dealing with 1x. And so if we look at this, we have the BH plus, and here's our amount, and it's 100% ionized. This is the part, and up here is the whole. Right? So it's completely ionized, and that's great because if we're analyzing this and our spectrometer or whatever is sensitive to the BH plus, then we've got all the signal. We've got as much signal as we can have possibly in this situation. So essentially 0 unprotonated bases left, but with our equilibrium calculations, we can calculate it's just a tiny number. So it's 5 times 10 to the minus 11 molar. Really insignificant. Probably it'd be very difficult to detect any unprotonated base. We'll get into this next time about how pH is driven in the stomach and the colon. But notice the stomach is buffered from 1 to 3 pH, and the colon is 5 to 7. Actually, no, the small intestine's 5 to 7, and the colon 7 to 8. And so that's going to decide what's absorbed in the stomach or in the small intestine or the colon, because your bloodstream is aqueous. And so if you change the buffered pH system, then you're driving things. Le Chatelier's taxi is driving things into the bloodstream. And there's different stops along the way. And you get into the stomach, and he's like, pH 1, your stop, get in. We'll take you over to the bloodstream. And those things that are ionized at pH 1, like these bases, would go into the bloodstream. And then things that are acids would be deprotonated at a more basic pH. And so then those are deprotonated, they're negatively charged, they go into the bloodstream in the colon. And so this is pharmacology. This is how we understand why things absorb at different places in the body. Okay. So, my little alarm didn't go off. I was so excited about that. Music. That's okay. Oh, 8:55. Good. Let's talk this. Let me finish this real quick. So the bases are protonated and more soluble in the stomach. We get here to the colon and really the colon. So acids are deprotonated and more soluble. So if you think about just acetic acid, right, it's neutral, but you pull the proton off and now you have acetate anion. And again, aqueous isn't just positives, it's also negatives. So the water, the aqueous solution, can stabilize a negative charge, it can stabilize a positive charge. Organic solution can't. So what's the organic-y part? Well, all of the fats and things like that. The fat-soluble drugs are going to be neutral. The blood-soluble drugs are going to be charged. So you can drive things into the fat or into the blood depending upon the pH. And so then we have some absorption calculations, and these we'll have to wait till next time. Let me go ahead and get started. Pass these things down. There's truly of course, the mirror. Let's see what I got over here. Jessica. Okay, let me pull the key up on the screen. Oh, I left my mouse upstairs. I hate it when that happens.